Okay, so I have begun recording. And, let me share my Windows journal. Okay, so today's lecture is going to be on a couple of topics that are, are part of quantum computing in a broader sense. But some people would like to, categorize them as part of quantum communication uh, because they deal with the transporting information from one place to another place. And we will discuss two specific schemes. One is called quantum key distribution. But it's really a protocol for transmission of quantum information. It could be messages or anything else. But since it's a costly method, which means that it requires a lot of back and forth and uh, a protocol which uses a lot of overhead in transmitting a message. So the idea is that this scheme would most likely be used only for transmission of keys, the keys that can be used to encrypt and decrypt messages instead of transmitting the whole messages because of sheer overhead and complexity of the scheme. But really, it's a scheme for transmission of quantum information. But since mostly it's envisioned to be used uh, for uh, for distributing and the piece of information, which is uh, which we want to be kept secret, and because of that, it's envisioned only to be used for keys distribution. So that's why you see the name for this, but it doesn't mean that it can only be used for distribution of keys. It can be used to send any information that we want. So maybe another name for this thing is quantum secure communication. And it is only one of the protocol. And we will discuss it because it is the simplest that exploits the properties of quantum physics, but people have developed more elaborate and more advanced algorithms that use lesser overhead than this scheme. But they all rely on the fundamental principle that we will use in this scheme. The second thing that we will discuss related to this is that how to transmit a quantum state of a qubit from one place to another place, but by using classical bits. That we use classical channels, classical ones and zeros. We transmit only those classical information from one place to another place, but using those classical information, we plan on sending quantum state from one place to another place. This is called teleportation. And we will discuss both of them hopefully today. So let's begin with the first one, which is the quantum key distribution. It is also called BB84 because in 1984, Benioff and Bennett proposed this scheme for communication. So it's based on this fundamental principle of quantum physics. It's called no cloning theorem. So no cloning theorem says that if you have a certain quantum state and it is a certain qubit is in a certain quantum state. So the theorem says that you cannot copy this qubit state to another qubit state without disturbing this first one. So if you transmit this information to another qubit, the exact state to another qubit, there's no guarantee that the state of the previous qubit is going to be the same. If you want to preserve the qubit state of this qubit, then there's no guarantee that you will be able to copy this state to another qubit. So at one time, the qubit state described by phi s can only be either in this qubit or in the second qubit. So that's the no cloning theorem. I'm not going to, into proving this, but if you Google no cloning theorem, you can get, proofs on the web. So because of this, no cloning theorem, there are a lot of things that we can do quantum mechanically. First of all, we can use it to, transmit quantum information from one place to another place, because if we imagine, let's say, a bunch of photon going along an optical fiber or in free space, and we have encoded some qubit states on these photons, then if somebody, tries to intercept our message and tries to read these photon states, then there's a possibility that these photon states would be disturbed, and what we would get here will not exactly be the same as was transmitted here. This BB84 algorithm tries to exploit this disturbance of information because of interception to make sure that we are able to do secure communication. Because at the very least, when we know that information has been disturbed, somebody has to try to read it, we can discard it and try to send again. Okay, so this is basically the basic principle, and let me describe one more thing before I describe the BB84 protocol. So if I have a qubit state, let's say either 0 or 1, then if I try to measure this state in Z basis, so Z basis is 0 and 1 basis. So if this state is 0 already, when I will do measurement, after I do measurement, and we will only talk about what we call projective measurement, that after a measurement, the state is projected to one of the eigenstate of this measurement device instead of some other state. There are other types of measurements, but for all practical purposes, most of the measurements are projective measurements. Anyway, so if I measure it, and this is 0 state already, I will measure 0 state, and the state of this qubit would be 0 after the measurement. Similarly, if it is 1 already, and I do a measurement, the state would be 1 even after the measurement. So in this case, I didn't really disturb the state. Whatever the state was, I was lucky. I was measuring in Z basis, and the state after measurement was also the same. So, however, if my state, let's say, is the plus state is this state, and if I now do measurement in Z basis, then I will either measure 0 or I will measure 1 with a half probability. So half of the time the measurement would yield 0, the other half of the time the measurement would yield 1. So after measurement, we will either have 0 or we will have 1, which means that this state has been disturbed. The plus state has been projected to either 0 or 1 state. Similarly, if this 0 and 1 that was here, if instead of measuring in the Z basis, if we have tried to measure it in X basis, so X basis is where we project the state onto plus or minus basis. And it's very easy to, incorporate this measurement. We can have our state that we want to measure, apply the Hadamard transform, and then apply the regular Z measurement operator. Because if this was a zero state, this will be projected to, plus state, and if this was, plus state, this would be projected to zero state. And if I measure zero, we will say that it was a plus state. Similarly, if it was a minus state, and if we apply Hadamard, this would be 1, and we will measure 1. So we can construct these X basis operator, which measures in plus and minus Z basis. And if we have, 0 at the input at this X measurement operator, we will either get plus or minus, because we can write 0 as a superposition of plus and minus. Similarly, if we have 1 at the input, we will either measure plus or minus, because we can express 1 as a superposition of plus and minus, and so on. However, if the input was plus or minus, this will remain plus or minus. So when we are trying to measure in a certain basis, if the input is already in that basis, it will not be disturbed. But if the input is in another basis, the state would be disturbed after the measurement. So let's use this thing to construct a scheme for transmitting a square message. So the scheme is really simple. And it's like this. Suppose some Alice has a certain message that she wants to send over some channel, and the channel belongs to somebody else. I mean, it could be a public channel, or maybe, it's a channel that other people can easily intercept. So we would imagine that we want to send the message to someone, let's say Bob, from here to here. This channel is compromised in general, and that's actually the usual assumption in building secure communication algorithm, that we all always assume that whatever we are going to send from here, it could be intercepted by anybody along the way before it reaches the intended recipient. Okay, so this is the message that she wants to send. So the protocol is this, that she randomly chooses a basis. Let's say X, X, Z, 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 etc. Any random, sequence of X or Z bases. That's what she's going to choose. And then she encodes her message in this basis. So 1 in X basis will become 1. 0 in X basis will be encoded to 0 state. But 0, so the 0 1s are like Z bases. So 1 in X basis would go to minus state. 0 in X basis would be plus state. 0 in Z basis would be 0 state. 1 in Z basis is 1 state. 0 in Z basis is 0. 0 in Z basis is 0. So 0 in X basis is plus. 0 in X basis is plus. 1 in Z basis is minus, and so on. And this is the message that she sends. For example, she can choose photons for transmission. So maybe 0 and 1 represents, let's say, the polarization along x-axis is represented by state 0. Polarization along y-axis, maybe it's represented by 1. And maybe polarization along 45 angles, or maybe circular polarization states, that can be represented by plus or minus states. So after encoding these photons, or maybe some spins of electrons or other qubit, whatever, but most commonly these are photons for communication purposes. So this is the message that she encodes. She sends this message publicly over this channel. This is a secret which is known only to Alice, and this is a secret so far which is only known to Alice. This message is being sent over a public channel. So let's for the moment imagine that there's no interception. So the message goes to Bob. Now what Bob does is that Bob also chooses a random sequence of bases for measurement. For example, Bob says that I will measure the first qubit in Z bases, the second qubit in Z bases, the third qubit in Z bases, then X, Z, X, Z, X, Z, and so on. So this is now secret which is known to Bob only, that he chooses a random sequence of bases to make measurements on these qubits. So this minus in Z bases would be either a 0 or 1. Okay, so it can be 0 or 1 because this minus is a superposition of 0, 1, and in Z bases I measure either only 0 or 1. So this plus in Z bases again would be either 0 or 1. This 0 in Z bases would be 0. This 1 in X bases would be either plus or minus, because X measures either plus or minus. So, but this is 1, so this 1 is a superposition of plus minus. So the measurement could either be plus or minus. This 0 in Z bases would again be just 0, because in Z bases I measure only 0 or 1. Similarly, this 0 in X bases would be either plus or minus. Similarly, this plus in Z bases would be either 0 or 1, because it's plus and Z measures 0, 1. Similarly, this plus in X bases would be, but since X measure plus minus, so plus will be measured only 0. So this is what Bob measures. So here either 0, 1, 0, 1. So this definitely 0, this definitely 0, this definitely 0, and so on. Now, once Bob has done the measurements, then what Bob and Alice do, they exchange information on their choice of basis. They don't, yet share these measurement results or this message. What they do, that they, through the channel, Bob and Alice send each other the information on their basis. So Alice will send, for example, this basis to Bob, that I use this basis to encode the message. So now what Bob does, he says that, okay, so this is a place where my choice of basis and Alice's choice of basis was the same. So here, then this is X, so it is same here and here, and then this is XZ, XZ. So these are the places, and then you can continue where Bob has incidentally chosen the same basis as Alice. So what Bob does, that he keeps only this message where his choice of basis was exactly the same as Alice. Now Bob knows for sure, assuming that there was no interference, that this was the part of message that were in fact the same as was supposed to be sent by Alice. So Bob discards the rest of the bits. So Bob only keeps those bits that had the same basis as for Alice. And if there's no interference, so essentially the key has been, the information has been transmitted to Bob, and we can end it here. Okay, so in this case, the overhead, we can easily count that how many extra bits were sent, and by computing the probabilities of this incidence, that how many times the number of bases are going to be the same for Bob and Alice. So using this, we can work out how many bits would normally be transmitted in the message. However, to make sure that there's no interference, let's now analyze the impact of an eavesdropper. Suppose there is somebody who is trying to interfere in the message. So what this person does is there could be a couple of things. So first of all, let's just see that this person just tries to read off the messages. So this was the bit sequence that was being transmitted, and this eavesdropper was trying to read them off. So which means essentially that this E was measuring these bits. So suppose this E doesn't measure all of the bit. She measures only, some of the bits. For example, this, let's say the first bit. So when this person measures this first bit, she will have to decide which basis to use, either Z basis, X basis, or some other basis. So unless she uses X basis, she is going to disturb the state, because this is a minus state. So if she uses X basis, she will measure minus state, and the bit will still not be disturbed, and there won't be any interference in the message. But if she uses some other basis, and since the basis is a random sequence of X and Z, and there's a 50% probability, let's say if E only uses either X and Z, that she's going to disturb this bit, because if she uses Z basis, this minus is going to be transmitted to either 0 or 1. But anyway, so since this is a bit where Bob is using a different basis than Alice, so this is going to be discarded anyway. So this doesn't matter. However, if E measures this third bit, which is 0 here, and since this is the bit where Bob also has the same basis, if Eves disturbs this bit, then there's a probability that Bob will get a different message than what Alice intended, and Eve will have might have a knowledge of the bit that was being transmitted by Alice. So there's a possibility that because of interference of somebody who's trying to read off the information, that some of these bits would be corrupted. Okay, for example, you can say there's one that came later and so on. So there's a probability that some of these bits are corrupted. Now, to guard against this, what Bob and Alice does, they compare some number of their bits. For example, the message that they received was this 4-bit, and what they do, that they compare these 2 bits. So what Bob does, Bob sends these 2 bits to Alice and also their location. So Alice compares with her own message that what she transmitted as 0 and 0, sorry, not this 0, but this 0. If these 2 zeros are the same as these 2 zeros, it means that there wasn't interference, at least in these 2 bits. So there is some probability that the other bits are also better. So what Bob can send, then Alice sends a message back to Bob that those bits were okay, they were not disturbed. So Bob can keep these 2 as securely transmitted message. But you can still see that there's still a probability that Eve might have not disturbed these bits, but perhaps these bits. So what happens that this communication protocol is designed to make sure that the bits that were sent are accurate with a certain probability. So we can work out those probabilities by, let's say, if there are 100 bits transmitted to Bob, maybe Bob and Alice can use 90 of those bits just to match with each other, that if there was any interference or not, and just keep the remaining 10 bits as part of the message that is being transmitted. So, and discard those 90 bits that they use for comparison, whether there was interference or not. So using this scheme, we can build a scheme that would be accurate to any desired level of probability of accuracy that we want. All we have to do is add more and more overheads. So any question on this BB884 scheme?
Hello, sir. Sir, Bob and Alice were comparing bits, overhead bits. Were they comparing it with classical? These were classical bits, so they were comparing it with classical channel.
They can do that comparison either over quantum or classical channel.
Sure. And sir, my second question is, if let's say E want to destroy the whole message, he can read all the bits with any bits, and that's so all the message could be corrupted, and anyone can corrupt all the message with interference sitting at channel. So isn't it?
Yeah, so that's a probability. So you're exactly right. So if somebody is, interfering in the channel all the time, it means that channel is useless, because whatever you send, it gets corrupted. So you will either have to come up with another channel, another way of transmitting information, construct another channel, or simply forget transmission. Because in this way, we are assuming that the channel is somewhat faithful. It's not, 100% corrupted. Because if that is the case, nobody is going to use that channel, right?
And sir, how can we send plus state? Classically, we send 0 and 1 with 5 or 0 volts. How can we send plus or minus state, transfer from one place to another, these states?
So this information, this initial qubit, they are qubits. So they are not going to be sent, with 0 or 5 volts, because this is not classical information. So this minus, plus, 0, etc. These are qubits. So we will have to, if you think about electron states, if we are sending a stream of electrons, they would all have to have a spin up, let's say, or spin down for plus and minus, and a superposition of spin up and a down state for a superposition state. For photons, we can easily think of, in terms of polarization state. So photons can be horizontally or vertically polarized, and maybe they can also be, circularly polarized, which is a superposition of these two other states.
Sure, sir. Thank you.
Okay, if there's no other question, let's move to the second part. By the way, so right now, doing this type of communication is still very problematic, because even if there's no Eve present to interfere in the communication during transmission of qubits from one place to another place, there's an Eve sitting in every quantum computer right now, because our quantum computers are very noisy. And if you implement this even without any interference, some of the time the measurements that you do in exactly the same basis as Alice used to encode the message, you will still get an error. And your qubit, if 0 was encoded using Z basis, and then you measured the same qubit in Z basis, you might not get 0. There is a certain probability of getting 1. We have seen it in running several, programs earlier, that running on an actual quantum computer gave us an error. So with the hope that as quantum computers get better and better, this error will be reduced, but this error is always going to be there. So when we analyze this scheme for more realistic communication, we will not only have to include the impact of the channel interference, but also the impact of the noise of quantum computer that Alice is using for encoding and Bob is using for decoding. So communication would be only as good as the worst quantum computer used by either Alice or Bob for encoding and decoding.
Excuse me, sir. I just want to ask, in your expert opinion, we say that quantum computing, the whole academic world is kind of divided into two parts. Half of it says that it's not going to happen, and half of say it's going to happen. So in your expert opinion, in how many years are we going to expect a less noisy a tangible quantum computer? I know it's a difficult question, but for the sake of debate, what is the number?
First of all, I'm not really an expert on the hardware side, but what I have been gathering from a lot of webinars, and especially listening to several talks by people in IBM Qiskit is what I usually follow, and also few from other places. Uh, my guess is that the number of years probably are going to be still many. So for any higher number of good qubits, that it might be maybe a decade for 500 or 1000 excellent qubits. But if we just track the progress of qubits, we see that there is still an incremental progress every year in terms of quality of qubits and number of qubits. So from 25 to 30 to right now, IBM has a 57 qubit chip, and the quality is not as bad as last year. So there is going to be incremental progress, but still, I think it's gonna be a little bit, longer than most people would say that, okay, it's going to happen maybe next year or a year after.
I'm asking from a PhD student point of view. When an examiner asks you that this is something which is not tangible and I don't see it in next 20 and 30 years, and you're developing algorithms, when you're assuming that there will be quantum channels and all, so how can I give a well-rounded example which can satisfy that this is going to happen? So we have to be prepared for that. So how can I give
so this is actually an excellent question, that why should somebody spend time on this? So my personal answer to this is that physicists must spend time on this, because first of all, this is not something that is so far disproved that it can't be done. So there's a possibility, and since there's some promise, so this is something worthwhile to be investigated, to at least see if it can be done or not. So that's one thing. The second is this, that for applications in quantum physics, actually we may not even need a lot of qubits. Already there is a lot of work that now people can do, like an experimental physics work from their offices by accessing these very high quality quantum systems. So these quantum computers are nothing but, if you think in terms of atoms or other particles, these are like two-level systems that are provided to you. And for example, IBM's quantum computer, have a hardware level control. You can send in, let's say, different types of pulses. You can have different pulse shapes and see how the systems respond to them, and you can sort of do a very high quality quantum physics sitting right in your offices. That was only possible a few years ago if you have a very expensive quantum system sitting in your labs. So this is an experimental device, and that you can do right in your from your office. The second thing is this, there is actually very good work being done by Microsoft people. What they are trying to do is they are discovering even better classical algorithm inspired by the quantum algorithm. So because quantum algorithms give you another way of thinking about the problem, and they call it dequantizing. So some of the quantum algorithms, they have used the same inspiration and similar method to build even better classical algorithm. So it's actually something which goes against quantum computer, but that is also still a utility of thought and ingenuity that is going into building these new quantum algorithms. So even for computer scientists, there is something useful in terms of practical application right there. So in addition to this, the applications in quantum chemistry, where, for example, our goal is to simulate molecules which require only few tens of qubits, and maybe at most 100 something qubits. That is, in my personal opinion, is going to happen very, very soon, maybe in a couple of years, because we already have computers with 40-50 qubits of very good quality. So going to 100 or 100 plus is doesn't sound that far away. So I think in terms of quantum chemistry, where we are interested in simulating interacting quantum particles like different electrons or ions, that is going to happen very soon as well.
Okay, sir. Thank you so much. Thank you for the elaborate answer.
Yeah. But applications for example, Grover search algorithm or Shor's factoring algorithm, that I think are going to be taking maybe 10 years or more. Because that requires a lot of qubits to make it practical, to make it better than the classical computers.
Thank you, sir.
Okay, so thank you. And let's now talk about the second thing that we were discussing. It's teleportation. So the idea of teleportation is to send quantum state from one qubit to another qubit using classical channel. So previously we were sending actual qubits from one place to another place, for example, using photons, or maybe potentially using other quantum particle in future. But here we want to copy this state to another qubit. Of course, this would be destroyed. This qubit that is carrying this quantum state phi s, this will be destroyed, but it would be copied to another state. And we will not even read the state during this transmission. So there is some state over here. We don't know what state is, because if we know the state, this is essentially like measuring the state, which destroys the state itself. So there's some quantum state, and we want to copy it from one qubit to another qubit, and using some operations. And the information that is going to be required, it's only going to be classical information. So this thing not only have applications in terms of transmitting quantum state of something from one place to another place, but also has applications in quantum computers, because most of quantum computers, for example, they are designed like this, that there is qubits that are sitting close to each other, but the entangling operations are the controlled operations that happen between these, let's say, two qubits. They're only possible between nearby qubits. For example, this may be possible between these two, or these two, or these two. But when you are building a quantum algorithm which involves several qubits, you might want, at some point, a C0 operation, for example, between this qubit and this qubit. So how you do it? So you do it by doing a lot of juggling of things. For example, you temporarily transmit this qubit state to this qubit state, but before that you might have to retain this qubit state. So you, from here, you copy it to some auxiliary qubit, and then you bring this qubit here, you copy this state to this state, and then you perform this operation. Then probably, if you want, you might want to bring it back, and then you might want to take this qubit state back to this state. So we need this transmission of state from one place to another place, even on a quantum computer processor. So not only for communication, but also for quantum computing, this teleportation operation is very important. And actually, when you write an algorithm using Python, and you send it to, let's say, over cloud to an IBM computer, before the algorithm is executed, there's an intermediate processor which actually insert all of these sort of assembly level commands into your code, that whatever those shufflings and teleportation has to be done, it does. So you might be writing only few commands. Okay, perform C0 gate between qubit 1, qubit 2, and then C0 gate between qubit 1, qubit 3. But physically, that C0 between 1 and 3 might not be possible. So the assembler, which is hidden from us, that does insert all of these operations into it. And when the code goes to the actual hardware, all of these things happen over there. Okay, so let's discuss this teleportation sort of algorithm. And this, for me, actually is more important in terms of instruction, because this also gives us an idea how we think about new circuits and new ways, and how do we manipulate, use the math to come up with these schemes. So what I'm going to do is give you the algorithm first, and then explain to you later why it works the way it is, and how you can, probably bring work up other ways of doing these kinds of operation. So the algorithm is like this. Let's suppose you have certain state phi s and some qubit that we want to transmit to some other place. And what we do, we prepare two qubits. Let's call them qubits A and B. And then we prepare a Bell state, a 0-0 Bell state of those qubits. And just, for the sake of completeness, let me review. 0-0 Bell state was this maximally entangled state of 0-0-1-1. 0-1 was 0-1 plus 1-0. 1-0 was 0-0 minus 1-1, and 1-1 as 1 over square root 2, 0-1 minus 1-0. So let's say there are two qubits that share this Bell state. And what we do that out of those two qubits, we do a measurement in Bell basis between one of these qubits, let's say qubit A and this qubit S. And the Bell measurement is done by inverting the Bell operation. So remember, we have the entangling circuit like this that prepares, a Bell state between, let's say, if we initialize this to 0-0, you can prepare this psi 0-0 state, entangled state between two qubits. So the inverse of this would be a circuit which is equivalent to measuring in the Bell basis. So this essentially, if the 0-0, if the psi 0-0 is inputted here, you will get 0-0. If psi 0-1 is inputted here, you will get 0-1. If psi 1-0 is inputted here, you will get 1-0, and so on. So out of these two entangled qubit, one is used with this phi s to make this measurement in what we call Bell basis. And then let's say you do this measurements and something comes out, we call it I, and you measure this one, and let's say some classical bit comes out, which we call J. Then based on these results, what we do is this, that we perform first an X gate, a NOT gate, controlled by this qubit. And then we performed a Z gate controlled by this first input. And over here, what we get is this state phi s right over here. So let me explain again that what is physically happening, and then we will see that where the circuit comes from. So let's say there are three qubits. So this is S qubit. These two are auxiliary qubit AB. So our goal is to transport the state of this qubit to this qubit. That's our goal. So what we first do, we do an entangling operation between these two and prepare these two qubits in psi 0-0 state. And once we have prepared these two qubits in psi 0-0 state, what we do a Bell measurement of these two qubits like this, that there is a C naught, that with respect to this, there's a NOT gate, and then there's a Hadamard gate on this, and then there are measurement of these two qubits. So we are going to measure this, and we are going to measure this. And then based on the measurement of this qubit, we are going to perform an X gate. If the measurement comes 0, nothing happens. If the measurement comes 1, we apply an X gate to this. And then based on the measurement of this A qubit, we perform Z gate if the measurement gives us 1, and if we do nothing, if the measurement gives us 0. And we claim that at the end of all of this, this qubit will be in state phi S. And of course, this qubit would be destroyed, because when we are doing measurement on this, it's either going to be 0 or 1. So the state over here is destroyed, and state over here is something. So similarly, this would be also be in 0, 1 state after measurement, because there's a measurement happening in this A state as well. So this is an algorithm, and unfortunately, it's not easy to see that it works as we are claiming unless we do some math. So let me do that math, and hopefully this will make clear that that the circuit is doing what we are saying it's doing.
Can you slide up for a second? I'm so sorry.
Sure.
Thank you so much.
Okay. All right. So this is our starting point. We have our qubit S in state 5, and then we have our qubits A, B in state 0, 0, which means that I can write it like this. This phi S, let's say this is some alpha 0 plus beta 1. So this phi S is a general state. I'm taking it to be any state alpha 0 plus beta 1. Of course, alpha square plus beta square is 1 because it's a normalized state. And then this psi 0, 0 state is 1 over square root 2 into 0, 0 plus 1, 1. And just for the sake of clarity, I'm going to write this AB subscript this time to make sure that, and let me write this, S over here, that this belongs to S qubit and this A and B qubit. So if we carry the multiplication, this would become 1 over square root 2. So this 0 multiplies with 0, 0, we get alpha 0, 0, 0 SAB. This is the state of S, A, and B. So this 0 multiplies with 1, 1. So I get, yes, Fizan, you have a question? Mohammed Fizan, I saw that you raised hand. Okay, so maybe it was an error. So this alpha 0 multiplies with 1, 1. So I get alpha 0, 1, 1. And then this beta 1 multiplies with 0, 0. So I get beta 1, 0, 0 SAB. And then beta state multiplies with 1, 1. So I get beta 1, 1, 1 SAB. So this is what we get after we carry out this multiplication. Let me write it over here again, because I will need to write it down. So alpha 0, 0 plus alpha 0, 1, 1 plus beta 1, 0, 0 plus beta 1, 1, 1. Okay, now I'm going to, do something like this, that I'm going to multiply this thing with 2, and I have divided with 2, so everything is okay. So when I multiply this first state with 2, this becomes 2 alpha 0, 0. And instead of writing it 2 alpha 0, 0, let me write it as alpha 0, 0 plus alpha 0, 0. Similarly, this 2 alpha 0, 1, 1, let me write it as alpha 0, 1, 1 plus alpha 0, 1, 1. Similarly, this beta 1, 0, 0. Let me write it beta 1, 0, 0 plus beta 1, 0, 0. And the beta 1, 1, when I make it twice, let me write it simply twice instead of writing 2, beta 1, 1, 1. Now, I'm going to first write it and then I'll tell you why I did like this. So let me add this term plus alpha 110 and also subtract it. And I did it because when I wrote it this alpha 110, I will be able to take this 0 common from the right side, and the state on the left would become 0, 0 plus 1, 1. But I also have to preserve the equality over here. So whatever I added, I subtracted as well. And this time I'll be able to take this 0 common from the right side, and I'll be left with state 0, 0 minus 1, 1 in the inside. Similarly, let me add beta 0, 1, 0 and subtract beta 0, 1, 0. So this will also help me take common this 0, beta 0 on the right side, and then I'll be left with 1, 0 minus 0, 1 here and 1, 0 minus 0, 1 over here. Similarly, over here, let's add alpha 101 and subtract alpha 101. So I'll be able to take this 1 common from the right side. And over here, let me add beta 001 and subtract beta 001. Now I can, 1 over 2 under root 2. So from this, I get 0, 0 plus 1, 1 into alpha 0. From the second one, I get 0, 0 minus 1, 1 into alpha 0. From this one, we will get 0, 1 plus 1, 0 into alpha 1, and the second one plus 0, 1 minus 1, 0 into alpha 1. Similarly, from here, we will get 1, 0 plus 0, 1 into beta 0, and then over here 1, 0 minus 0, 1 into beta 0. So from this one, this would be 1, 1 plus 0, 0 into beta 1, and from this I will get minus 0, 0 minus 1, 1. So this is 1, 1 minus 0, 0, but I took minus common out, so this becomes 0, 0 minus 1, 1, and then this 1 on the right side is common, so this is beta 1. Now I can combine these things in such a way that I get Bell states on the left side and something on the right side. For example, if you see this thing, this is 0, 0 plus 1, 1, and this is 0, 0 plus 1, 1. So from this and this, we can take, and actually let me remove square root 2 from here, because I can put square root under this, and into this is alpha of 0 plus beta of 1, alpha of 0 plus beta 1. So similarly for this state, this is 0, 0 minus 1, 1. So this is 0, 0 minus 1, 1. And we can see that this becomes 0, 0 minus 1, 1 over square root 2. So I have alpha 0 and I have beta 1 with a minus sign. And from this one, This is 1 0 plus 0 1. So this is also 0 1 plus 1 0 alpha 1. So here I get 0 1 plus 1 0 into alpha of 1 plus beta of 0. And when I use this one and this one, this is 0 1 minus 1 0, and this is 1 0 minus 0 1. So let me see what is the definition that we have. So 0 1 minus 1 0 is this state. So so 0 1 minus 1 0. So this will come with plus sign, and no, so this will come with minus sign. I can take minus common from here, and then 0 1 minus 1 0 will come here. So I have 0 1 minus 1 0 into alpha of 1 minus beta of 0. Alpha of 1 minus beta of 0. So now we see that we have Bell states on left side and some state on the right side, and we have linear combination. So let me use the symbols that we already had. This is nothing but 0 0 Bell state. So I get half psi SA, because these are the left two qubit, the S and A qubit. So for the state psi 0 0, I got this alpha 0 plus beta 1 state. Alpha 0 plus beta 1. And then for the this 0 0 minus 1 1 state, what is this? 0 0 minus 1 1. So 0 0 minus 1 1 is this 1 0 state. Plus psi 1 0, alpha 0 minus beta 1, alpha 0 minus beta 1. So this one is the 0 1 state, and this is alpha 1 plus beta 0, and this last one is the psi 1 1 state. One one alpha 1 minus beta 0. Now this alpha 0 beta 1 is nothing but phi s. But it has now gone on the rightmost qubit, which is the B qubit. So this alpha 0 beta 1 was our state. So this alpha 0 and minus beta 1 is nothing but a phi state operated with a Z gate, because what does Z do? Z flips the sign of one state. So this psi 1 0 will give us a phi state that has been operated on by the Z gate. So this is psi SA01 state, and this is nothing but a state obtained by operating X gate on phi state, because this 0 has gone to 1 and 1 has gone to 0. So this is nothing but X gate operated on phi state. Similarly, the last, this state is nothing but that is obtained by first operating a Z gate, because when you operate Z gate, you will get this state. And on this one, when you operate Z gate, this 1 goes to 0 and goes to 1. So you first operate Z gate on phi, and then you operate X gate. And this is what you get. So this is the state that we just got by manipulating. We haven't done anything. So this is a state that is still only up to this point. I just rewrote them in a certain way that the phi state has come on this side, and on this side there's a several possible combinations of psi and phi state. Now this is the measurement in Bell basis, because if there is a psi 00 state here, this will give us 00 here. If there's a psi 01 state here, this will give us 01. If there's a psi 10 state here, this will give us 10 at the output. And if there's a psi 11, this will give us 11 at the output. So which means that this is my input state to the circuit. So if we now do measurement on the SA qubits, these are the first two qubits, there's a possibility that we either get 00, which means that this was this state, so this will collapse to this state. So it means if we get 00, we don't need to do anything to B state, and whatever is on the B qubit, this is already phi. And if we do measurement on SA and we get a result 10, which means that the state is collapsing to psi 10 state. So it means on the other side, we have Z phi B state. So from Z phi B, if I want to get phi B, phi state on the B qubit, what should I do? I should apply another Z, because Z into Z is Z square, and which is identity. So I will get phi B back. So that's why this first result 1 is controlling whether I apply a Z gate or not. And then similarly, if we get a result 01, it means on the other qubit, X phi B was present, which means that to get phi, I should apply an X gate, because X into X would be X square, which is identity. So I should have phi on the B qubit. And if our measurement gives us 1, 1, it means that the state collapse on SNA to psi SA. So which means that I got XZ. So if I have XZ over here, how do I get phi from it? I first apply an X gate and then apply a Z gate, because when I apply X and Z, this is XX square identity, and then ZZ square identity, this will become X. So I should first apply X and then apply Z, controlled by these two qubits. And that's why you see that I first have an X gate and then I have a Z gate. And these are being controlled by the measurements I and J over here. And you can also see that if we, instead of preparing these two qubits in the entangled state 00, if you want to prepare it in entangled state 01, then this would be somewhat different. And this would actually be different. You will have different operations with different controls if you share the state 01. Similarly, if you share another entangled state between these two, like 1, 1, you will have yet another set of operation, and you can easily work out. All you have to do is start with the state that you have shared between the other two qubit and the state that you want to transmit, and at the end you have to rewrite it in this certain way so that you can find out that if state collapses to psi 00, what the other state would be, and how do you what do you operate on to get phi out of that. Any questions? If not, let me show you an implementation of this teleportation circuit. And this is actually a notebook that I have already shared. It's notebook number 3. Okay. So if you go to the notebook number 3, at the end, there is this teleportation circuit, but let me, walk you through that. So we start from importing, and then this is something that we have already discussed. This is also something that we have already discussed. Okay, so this is that entangling circuit, because this is a Hadamard and a C0. And just as an example, we can see it here that if we start from 0, 0, we can get to this, 0, 0, psi 0, 0 state because of, so no, this is, so this starts from as evolve my circuit. There's a Hadamard. Yeah, so from 0, 0, we can go to the 0, 1 state, from to the 0, 0 state. Now here we can see the measurement. So we can initialize, if we initial this state to 1, 2, and then I apply Hadamard and Cx. Let's see what it does. And we can measure this 0, 1. We can measure this 0 and 1 and 2 qubits and put the information onto classical 0, 1 and 2 qubits. So when we execute it, so they're just this third qubit which is not doing anything, this Q2. So this 0, 0 that you see on the first part, this is just this idle sitting qubit. And this is, we see that since this circuit is initialized to 0, 0 in the beginning, we get this 0, 0 and 1, 1, the equal superposition 0.5, 0.4, 0.5, 0.5 on both. So this is like 1 over square root 0, 0 plus 1, 1 state. Anyway, so here is the demonstration for this teleportation circuit. You see that I have an arbitrary state psi that I have initialized to square root of 0.7 and square root of 0.3, because when you add the square root of this number, this will be 0.7 plus 0.3, so which is equal to 1. This is normalized state. And the first part that you see here is the preparation of psi 0, 0 state. So this Hadamard and C0, they are preparing a psi 0, 0 state from Q1 and Q2, because I want to copy this Q0 state onto Q2. So once I have prepared this psi 0, 0 state, this is the measurement in Bell basis, because this is the inverse of this entangling circuit. And once we have that, so I was just talking to you just before that you can do a measurement after this entangling in the Bell basis. And once you measure, you can decide an X gate with respect to this second qubit. So this is a C control X gate, and then you will have to apply a Z gate with respect to this first one. So the control Z gate. So here I have implemented control Z gate with control X and Hadamard, simply because let me just discuss one more point. That Hadamard X Hadamard is actually Z. So we can use control Z, but we can also use control X, in between the Hadamard. So that just implements a control X, a control Z gate. Let me share screen again. Okay, so can you see this Jupyter notebook again?
Yes, sir.
Okay, good. So this is the circuit, and let's see how we can see the operation that is happening. So I'm first simulating it using state vector simulator. So when we start, our qubit 0 is in 0 state, our qubit 1 is 1 state, and our qubit 2, you can see that it is in that desired state that we wanted it to be, right? Because we started this qubit 0 in this superposition state with alpha as square root 0.7 and beta as square root 0.3. But at the end of this circuit, we see that this qubit 0, qubit 1, they are in 0, 0 state, and qubit 2 is in the state that we want it to be. This is the superposition state. Let me run it again. And we see the same result. Let's now see the visualization on Q sphere. So this is, we don't need to discuss this. This is something that we have already discussed. Okay, so let me show it in terms of measurements. So I now have placed a measurement at the Q2, at the end of Q2, because by measuring using a simulator, we can see that our state has been transported to the state that we want. We wanted to copy this 0.83, 0.54 state, which is essentially 0.7, 0.3. And once we measure, we see that the probabilities match 0.3 and 0.3 that we want. And we can make this, probability even better by increasing the number of shots. So any question on teleportation? Or overall on the course?
I would just like to thank you for the course. In the previous course, I actually requested Dr. Sabi to have such kind of course in which we can have a hands-on experience on this. Unfortunately, I don't have a background in Python, but even then it was very elaborative and I was able to grasp the basic concepts. So thank you very much.
Thank you. So if there are not any other questions, I would like to thank all of you to hang on till the end, and I hope that you have gotten some idea of how quantum computer programming works, and hopefully you'll be able to build on this thing in future and learn many more things on your own. So I think Mohsana will be sharing a feedback form with you later on, and I would like to request you to do a candid feedback so that we can improve its offering for the next time if we plan on doing it again.
Thank you, sir. Sir, can we just ask a few questions whenever we are going through literature in future?
Sure, anytime. Just please send me an email and I would be more than happy to talk to you or respond to you.
Sure, sure.
I'd like to add some closing remarks. I'd like to thank everyone on behalf of the Khwarizmi Science Society as well for joining the course, for being so regular, even though we understand that everyone is very busy with their schedules and it's difficult to make time for classes during weekdays. So thank you all of you. And I'd also like to thank Dr. Faryad for putting in so much effort and time in these lectures, and it clearly shows the amount of effort that is put in, and we really hope that it's been helpful for you. And like Sir said, that I'm shortly going to be sharing a feedback form with all of you, so kindly fill that. And as for the certificates, I'll try my best to send them out in 2 days. Don't worry too much about the eligibility criteria. As far as you've attended like 6-7 classes or more than that, you're going to get a certificate. So we really do hope that's been a useful experience for you, and all of you have the link for the playlist and the videos, so you can obviously refer back to them. And if there's anything else that you'd like to send a feedback on, which is not covered in the form, then you can let me know individually. And like Dr. Faryad said, he'll be open for any discussions and questions in the future as well. So thank you, sir, and thank you, everyone.
Thank you very much.